Hello and welcome to week 5, lecture 3 of CO 442642 graph theory. Today we'll be discussing coloring graphs on surfaces. So to remind you about surfaces from our last lecture, here's a brief summary. So we talked about the classification of surfaces theorem, that there are two types of surfaces, the orientable ones, which are obtained from the sphere by adding handles, and NK, the non-orientable ones, which are obtained from the sphere by adding at least one, but more generally k, cross-caps. So these were the two types of surfaces. We discussed that theorem. We also at the end discussed the Euler genus of a surface as being equal to 2h plus k, where h would be the number of handles and k would be the number of cross-caps. And then we discussed the Euler's formula for surfaces, that if G is a graph embedded in a surface sigma, then V minus E plus F is equal to 1 plus the number of components minus this Euler genus. And that's why we define the Euler genus as such to make this formula work. And then of course we get the obvious corollary that if G is a graph embedded in a surface sigma, then E is in most 3 parentheses V minus 2 plus genus, end parentheses. So that graphs on surfaces have a relatively few number of edges, a linear number of edges in a sense, at least if they're large, but you could actually embed complete graphs. You can, again, any graph embeds on some surface. So that's for surfaces, but now let's talk about coloring graphs on surfaces. So the fundamental problem here, which is called the map color problem, is for each surface sigma, what is the maximum chromatic number of graphs embeddable in sigma? So generalizing the question from the plane now to all surfaces. So for any surface, what's this maximum chromatic number? What is the best upper bound we can have? Well, we know one answer from last time, or a week ago, that when sigma is the sphere, the answer is 4 by the 4-color theorem. So the 4-color theorem was eventually proved by Appel and Haken, resolving this question, that 4 is the right number for the plane, but that plane's not a surface again because it's not compact, but equivalently for the sphere. Okay, what about for surfaces of larger genus? Well, what should be the answer? So maybe you know this one. Actually, this has a more classical answer. There's a theorem from Haywoods from 1890, so all the way back in the 19th century, that if G is a graph embedded in a surface sigma with G at least 1, then chi is at most 7 plus the square root of 1 plus 24, the Euler genus, all over 2. So Haywoods is basically given an upper bound, a pretty decent upper bound, for all surfaces other than the sphere back in 1890. So let's call this the Haywoods number of a surface, and we'll actually round down to make it an integer, since coloring chromatic number has to be an integer. And this is generally referred to as Haywoods Formula. So just maybe if you're not used to this, let's just work a couple examples. So what happens when you're the sphere? When G is 0, you get 7 plus the square root of 1 over 2, which is 4, which actually does accord with the answer from the 4-color theorem. He just didn't prove, of course, the 4-color theorem back then. What about for n1, the projective plane? Well, G is 1, so you get 7 plus the square root of 25, which is 5, over 2, which gives you 6, so that's a nice number. When you're the torus, that's S1, or N2, the Klein bottle, genus is 2 there, so you get 7 plus the square root of 49, which is also 7, all over 2, which is 7. And so you get these values, and then the numbers get more weird and they're not always integer, but at least the first few ones are nice. So just mentioning that, what the answer is for small genus surfaces. And to prove Haywoods formula, we'll just go ahead and show that if G, we'll prove this nice little lemma, that if G is embeddable in a surface sigma with G of sigma at least 1, then the minimum degree is at most the Haywoods number minus 1. So let's prove this lemma. So if you haven't seen it before, I'll just run through it quickly because it's just a simple application of Euler's formula. If the genus is 1, then E is at most 3V minus 3 by Euler's. And if you think about what that means, it means there's a vertex of degree at most 5, which is indeed 6 minus 1, the Haywoods number of the projective plane. So we can assume that G is at least 2, and therefore we assume that delta is at least 6. Otherwise, there's nothing to show. For G at least 2, the Haywoods numbers are always at least 7. And so if the minimum degree was too small, we'd have nothing to show. We'd already be done. So we assume that. Then we use Euler's formula. By Euler's formula and the handshaking lemma, well, but we know now we know that twice the number of edges, which is the sum of the degree by handshaking, is at least delta v, but it's also at most 6v minus 12 plus 6g by Euler's. So if you rearrange this, you see that delta minus 6 times v is at most 6g minus 12. Okay, great. What can we do with that? Well, this is where we use two things. That delta minus 6 is positive, or non-negative rather, and that v is at least delta plus 1. The number of vertices in the graph have to be at least the minimum degree plus 1. So then if we combine those two, that left side is actually strictly at least as large as delta minus 6 delta plus 1, which then if we expand and rearrange, this becomes delta squared minus 5 delta plus 6 minus 6g is at most 0. And then if you solve for the roots of this quadratic equation, it turns out then the larger root you get is exactly Haywoods minus 1, which then establishes the bound. So that's the lemma. Then what can you do with that? Well, by the lemma, it follows that a graph embeddable on sigma, if g is at least 1, is h of sigma minus 1 degenerate. And hence that it's h of sigma colorable by greedy, right? So we know the minimum degree of the graph is h of sigma minus 1, this Hayward number minus 1. But of course, it's actually, every subgraph has that property because all subgraphs are also embeddable. And so then you actually get this degeneracy. And from that, you get coloring. So kind of greedily, inductively coloring, as we've discussed before. All right, so that concludes proving Haywoods. Then where do you go? Well, that's just an upper bound. So there became a conjecture by Haywood in 1890 that for all surfaces sigma with g at least 1, there exists a graph G embeddable in sigma with chi equal to h, which is also true for the sphere because K4 embeds and such. But more generally, Haywood was conjecturing that this is actually tight, that there is always a graph that attains this Haywood number, and so that's really the answer to the map color problem. So what was known and what was proved about this over the years? Well, first off, Franklin in 1930 showed that strangely this is false for the Klein bottle. That for the Klein bottle, it turns out that K7, really the only graph that would be an option, does not embed on the Klein bottle even though it embeds on the torus. Very strange. And use that then to compute that actually chi must be at most 6 for all graphs embeddable in the Klein bottle. So the Klein bottle is an exception to Haywood's conjecture. So then the question became, okay, maybe the Klein bottle is the only exception. And as it turns out, this is true. So Ringel and Youngs in 1968 proved that the Haywood's conjecture is true for all other surfaces sigma. And they showed that this more specifically by showing the complete graph of the Haywood order number embeds for all other sigma. And so it's really not a coloring theorem of theirs, it's a topological graph theory theorem, it's an embedding theorem. So you have to actually construct these embeddings. And 1968 is also a bit of a lie there in that the work had started in the 50s and it was by them and some other co-authors, each kind of taking cases. So how do you do this more generally? It turns out that given the parameters of complete graphs, it's useful somehow to look by what the genus is modulo 12. And over the years, they would prove cases. So they'd prove all surfaces with genus 1 modulo 12, and then 4 modulo 12, and fill them in. And then there were some exceptional numbers that they'd covered, you know, almost all of the 1 by 12 case or something, except for 13 or 25 or things like that. And so eventually, though, in 1968, this decade's worth of work was completed in which they had done all the cases. And so it's attributed to them in 1968. The Ringel-Youngs theorem is what it would be now called, proving Haywood's conjecture. Of course, except for this Klein bottle, which is just a strange fact of life, that the Klein, or math, or the world, that the Klein bottle is somehow this grand exception. So that was Haywood's conjecture. So now, where do we go from there? So, right, we've answered the fundamental question of coloring graphs on surfaces. We asked what the maximum was, and Haywood nicely used Euler's to provide an upper bound, and then Frankel, and then more really Ringel and Youngs completed the answer for all the surfaces, and then the four-color theorem topped it off by doing the answer for the sphere. So we've done everything, right? We've answered all the questions one could ask about coloring graphs on surfaces. Well, no, right? You shouldn't, again, be happy as a mathematician with just that answer. Maybe that's somehow the wrong question. Maybe there are other questions. So we looked at this with coloring plane graphs and what more could be asked. So let's look at this for surfaces. So I'd like to introduce you to the modern paradigm of coloring graphs on surfaces as introduced by Thomson in the 1990s. So I think it's very nice. And it kind of says maybe that old question, the old thoughts from Haywood and the Ringle-Youngs are nice, but maybe they're the wrong question somehow. Because perhaps most graphs embeddable on a surface have small chromatic number. What do I mean by small? Like even independent of genus, like 100 or 10. The question is, what is most? I mean, clearly there are graphs, these large cliques, that do not color, but maybe they're somehow the only reasons. It's these ones or the small ones. So let me give you some questions that would maybe try to formalize this. So maybe we could ask, for what k in sigma are there only somehow finitely many reasons that graphs embeddable in sigma are not k colorable? And I'll get into that more, but somehow maybe you could think of a reason as containing this large clique. Of course you could have isolated vertices and such, but somehow maybe that's one reason. And maybe there could be more reasons, but it'd be nice if there's somehow were a finite list of reasons. Okay, if you're not happy with that one, here's a different take. You could ask for what k in sigma are all locally planar graphs embedded in sigma k colorable. So maybe the problem, again, is that with these large cliques embedding is somehow they're using up a lot of the surface. They're not a typical graph on a surface. Maybe you would think a typical graph would kind of be locally planar. So around any vertex it kind of really looks like a planar thing, and the use of the surface is more just kind of around somehow the edges, right? It's just sporadic how it uses the cross caps and the handles. And so if it was local enough, planar, then maybe it'd be colorable for even something independent of genus. So that was another nice take, another approach. And finally, there's a third question I think is nice, is, for what k in sigma does there exist a polynomial time algorithm to decide if graphs embeddable in sigma are k colorable? So as we know, coloring is hard, and it'd be hard to decide if you're 3 colorable and even on the plane, but maybe we could actually kind of ask, maybe for larger k it's not, and for what k would that work, right? I mean, for the plane, there is a polynomial time algorithm to decide 4 colorability. The answer is just yes for all graphs by the 4-color theorem. And so via the Haywoods, that would also be true for, of course, for large enough k, but maybe we can make that k independent of the genus. So 3 kind of nice approaches. Maybe there's only finitely many reasons, or maybe if you're locally planar enough, then you're colorable, or maybe, well, at least maybe it's easy somehow to decide this. And of course, you can maybe see that all of these are a bit interrelated, and we'll go through each one and talk about how they might be related a bit. So let's begin with the first question. So what do I mean by a reason? Well, it turns out there's a nice notion called a critical graph, introduced by Dirac in the 1950s. So we say a graph G is k-critical if G has no k-1 coloring, but every proper subgraph of G does. So for example, cliques and odd cycles, or odd cycles are 3 critical, cliques are more generally kn is n critical, etc. And why is this a nice definition? Well, coloring is a monotone property, right? If you can color, then every subgraph colors, right? If G is k colorable, then every subgraph is. So it makes sense to look at the minimally, non-k-1 colorable graphs. And that would exactly be the k-critical ones. And so it's very natural to look at these, and maybe somewhat unfortunately, it's called k-critical, which makes sense because the chromatic number is k, but really it's about k-1 coloring. So if we maybe had a redo, I would call it critical for k-1 coloring, but we'll just use the definitions as they were before. So that's k-critical. And what actually was shown after kind of Ringle-Youngs, first by Dirac and then Albertson and Hutchinson, so Dirac in 52 and Albertson and Hutchinson in 78, showed that the complete graph, the kh of sigma, is the only h of sigma critical graph embeddable in sigma. So it's the only reason that a graph actually attains the Haywood number. So that kind of going to that first question, these reasons. So instead of reasons, we'll look to critical graphs. That would be the reason for coloring. So Dirac had done most of the cases, and Alberts and Hutchinson completed the cases, which makes sense because, after the Ringel-Young's theorem. Okay, so that it was nice, but then we can reformulate our question more generally, as asked by Thomason, for what k and sigma do there exist only finitely many k-critical graphs embeddable in sigma? So could this even be true for much smaller k? And it turns out the answer is yes. So it's yes for, well, k at least 8, it turns out, and this was by Dirac in 53, showed that if you just use Euler's formula, that same kind of computation, k-critical graphs have to have min degree k minus 1, it turns out that they have a bounded size coming from Euler's formula, right? Euler's formula is somehow suggesting other than that plus g factor, you're mostly degree 6s at most, and 8 critical graphs have min degree at least 7, so there just can't be too many such vertices. So that's not too hard. And then Galai in 63 showed the answer is yes for k equals 7 with a little bit more. So he found somewhat of a reducible configuration, and you can use discharging and show that there are also only finitely many. And then in a very deep breakthrough, Thomason showed that this is also true for k equals 6, and that's a 80-plus page proof from 1997. So really, for 5 coloring, there are only finitely many reasons why you're not 5 color. There's only finitely many 6 critical graphs embeddable in any surface sigma. So is that tight then? Is that the best we could do? Maybe we could say, we could hope that the 4-color theorem somehow more generally holds in this sense, that there's only finitely many reasons why you're not 4-colorable. But the answer, sadly, there is no. So no for k equal 5 and sigma not the sphere. Thomason, via construction of Figs, showed there are infinitely many 5 critical graphs embeddable on surfaces other than the sphere. Okay, so that kind of answers that first question, the reasons, the critical. Let's look at the other two. So what about locally planar graphs? For what k and sigma are all locally planar graphs embedded in sigma k-colorable? Well, we have to define what locally planar means. So here's maybe one best way to do it is to define the edge width of G, which we'll take to be the length of the shortest non-contractible cycle. So you're an embedded graph. And remember we talked about contractible cycles, right? The ones that contract down to points, the bound disks, right? Well, so a good way to view somehow how much a graph uses the surface is by its non-contractible cycles, by those cycles that go around the handles and the cross-caps and such. And so if we take the length of the shortest one, having large edge width would kind of be the same as being kind of more locally planar. That from the viewpoint of any vertex, it seems like it doesn't see the non-contractibility, the handles and cross-caps part of the surface. So we could actually reformulate this question as for what k and sigma does there exist a w, such that all graphs embedded in sigma with edge width at least w are k-colorable. So maybe large enough edge width implies this. And so what is known here, well, here's a nice proposition, is that for a surface sigma, finally many k-critical graphs implies that locally planar graphs are k minus 1 color. So these two questions are actually related. If you could answer the critical one, the reasons one, you actually get a nice answer for this locally planar question. So I'll go ahead and prove that. If you want to pause and think about what the proof should be, you're welcome to, but I'll run through this quick, nice little proof. Well, proof. Let L be the list of k-critical graphs embedded in sigma. So give me this list. There's only a finite number of them. And then the trick is we let W, our width we want to proclaim, to be the maximum of the edge width of the graphs in the list L plus 1. Right? So we take this maximum, but we add 1 to it. Right? And since the list is finite, then we'll have a maximum. And then if the edge width is greater than at least W, then of a graph, not one from the list, then it turns out then there does not exist a graph from the list that's a subgraph, right? So if I take my edge width large enough, then I can't possibly contain these smaller graphs, because here I'm assuming, of course, which will be true by the 4-color theorem, that all these k-critical graphs would be non-planar, so if k is at least 5, say. But then if they're non-planar, they have to use some of the surface. So they have to have some kind of edge width, and then if they have some kind of edge width, then by taking it large enough, then all of them, you'll guarantee not to contain them. And so then if it doesn't contain anything from the list, it has to be k-1 colorable, right? It'd have to have one of those reasons if it wasn't colorable, but then if it had one of those reasons, those have small edge width, and so it would too would have small edge width. They would have a short non-contractible cycle. So that concludes that bit. We have a nice proposition relating the two, so let's plug that in. So then we know that locally planar graphs in sigma are 5 colorable by Thomason, right? Who showed that there are only finitely many 6 critical. So that kind of is the answer, right? Well, you might wonder, what is the edge width? You know, Thomason didn't actually work out explicit list, at least for, it's only known for small kind of surfaces, what the lists are, so we don't really have a good grasp, but it turns out the edge width is at least, if edge width is at least 2 to the omega of g, that would suffice. Thomason actually showed this in '93, a few years before his critical theorem, so somewhat independently. And then with Robin Thomas, we actually improved this to log g, which is tight. So there are graphs, kind of expander graphs, which embed and have log g edge width and would not be 5 colorable, but so this is tied up to the constant. So we figured that one out. And so now we actually know good bounds. What about for 4 colorable? The answer is no. So Thomason showed that, again, if you're not the sphere, there exist graphs of arbitrarily large edge width that are not 4 colorable. So really the best we can do. So it's something weird. The 4-color theorem is really specific to the plane, to surfaces. More generally, it turns out like this 5-color theorem more generally holds, and that's a rather deep theorem, that locally planar graphs are 5 colorable, but not 4, unfortunately. And if you don't like surfaces, here's actually a nice theorem, again with Robin, that shows you can get rid of the surface part. So this is very strange, is there exists C greater than 0, such that if you let G be a graph, if every subgraph of G of diameter at most C log V of G, so log n and the number of vertices, is planar, then G is 5 colorable. So you can actually show that if you're not, here we're not talking about graphs embedded on surfaces, just kind of if you're locally planar everywhere, if it's kind of the local neighborhoods of vertices are planar, then you're actually 5 colorable. And what would local, a good parameter would be kind of log n is the obvious choice. And it turns out then this is also tight, that for the Thomason's construction, those ones are kind of locally planar in this sense and also not 4 colorable. So again, there's some magic in the air there that somehow if graphs locally look planar, then they actually are 5 colorable, and that's a rather deep and hard theorem, but they are not 4 colorable. So again, the 4-color theorem is just very special. What about algorithms? So let's wrap up with that last kind of question, and then we'll talk a little bit more. For what k and sigma does there exist a polynomial time algorithm to decide if graphs embeddable in sigma are k colorable? Right, so we asked about this polytime algorithm. Well, proposition again, for a surface sigma, the finitely many k critical implies this polytime algorithm to decide k-1 colorability. So again, if there are only somehow finitely many reasons, that should mean it's easy to test. And so maybe pause and think through a proof of this if you want yourself. So it's again not very hard, we're going to do it. It's short and quick. So here we go. Well, proof, we let L be the list of k critical graphs embeddable in sigma. And what do? Well, for every h and L, you test if h is a subgraph of your graph G you're interested in deciding. Right? And then what happens? Well, if it's yes for some h, so if G contains some reason not to be k-1 colorable, then you return no. If otherwise, if it passed the test for every such h, you return yes, right? Then there is no reason. And you can really do this as an algorithm because there's a finite list. Okay, so that's good, but what's the running time of that algorithm? So you have to think about what's the running time of testing. I mean, it's finite, so there's just some, but so what does a one test cost? So maybe stop and think about that. Well, obviously it would run in at most v of g to the maximum number of vertices of h, of these graphs in your list time, right? So to test, a subgraph h, whether it's in G, you could just test all collection of vertices of that size and see if they have the subgraph. So it would be polytime where the exponent would depend on the list, which would depend on the surface. But actually, subgraph testing is linear time on a fixed surface. This is a nice result of Epstein from '99, showing that you could actually do this in linear time for each h, so you just have some constant out front that would depend on the list and the surface, but would actually be linear for any surface. So that's very nice. So we've seen now the connection answers to question 1 imply answer to question 3, so finally many reasons implying decision algorithms. So what does that mean? So again, if we plug in our results from Thomas, and we know that for a fixed surface, there's actually a linear time algorithm to decide if a graph embedded in sigma is 5 colorable, and so also for 6 and 7 and so on as well, because they also have finite lists. Okay, so that's true, but maybe you're not happy, because maybe you wonder, what is this algorithm? I mean, I'd have to know the list, which seems hard. It's only known for a few surfaces, so it's not really constructive. Well, technically that's not true, in the sense that I could pre-process the algorithm to, there are finite size, there are known bounds on them, to find the list and then use that. Of course, that'd be terribly expensive, but constant time. There are actually algorithms, though, that do this decision that are constructive, so they don't need to know the list. And more generally, actually, you might ask, can we actually, so we can decide whether it's colorable, but can you actually find the coloring if it exists? And this was actually done by Dvorak and Kobayashi in 2013, that there exists a V of G to the O of G, that's the genus algorithm, to find a 5 coloring if it exists. So what if you actually want to color it? You've decided it has the coloring, but you actually want a coloring. And just last year I improved this to a linear time algorithm, so that doesn't depend on the genus of the surface, at least in the exponent, it does as a constant down front. So actually we can find the colorings rather efficiently now. Okay, so that is for 5 coloring. What about, could you do better, right? So for the critical, we said no, you can't do 4. For locally planar, we said no, you can't get it to 4. What about algorithms? Well, strangely, there is an open problem, right? So for the sphere, it's always just yes, but what about the other surfaces? It's an open problem, and it seems very, very hard whether there exists a Polytime algorithm to decide if a graph embedded in sigma is 4 colorable. So we don't really know this for any other surfaces. So in that sense, it could be that the 4-color theorem really does accept that deciding 4 colorability on surfaces might actually not be hard. It might be Polytime doable. All right, so then let me just briefly finish up with 2 last things. So we've talked about algorithms locally planar and critical for coloring graphs. What about coloring graphs of larger girth? So if you remember our Groitch's theorem and Thomason's girth 5 theorem and things, what about graphs with larger girth, triangle-free, girth at least 5? You could ask all these same questions, and there the answers are also known. So I'll just run through them. Well, what about the finitely many k critical graphs? That's yes for k is at least 5 and triangle-free. So when you're triangle-free and you want to do 4 coloring, that was easy in the plane, and so it's actually fairly easy to prove the finitely many here, and that would give you locally planar and algorithms as well. It is no, though, when k is 4 and triangle-free, and you're not the sphere, right? So for the sphere, there aren't any 4 critical triangle-free by Groitch's. For anything else, the answer is no, and that's a result of Thomason. So you can't get the finitely many there, but then you could think about what if you go higher girth. So girth 5, the answer is yes for k equal 4. So there are only finitely many 4 critical girth at least 5 graphs, and that's a result of Thomason from 03, and it's a 50+ page proof, so also very hard. And so, but at least that's a satisfying answer, that the answer is yes. So 3 coloring girth 5 graphs is actually somewhat doable then. Well, let's just return, though, to the triangle-free. So we said no to the finitely many critical when you're doing 3 coloring, and 4 coloring is easy. What about locally planar triangle-free graphs and algorithms? Well, these were actually both resolved by Dvorak, Kroll, and Thomas. So it turns out locally planar triangle-free graphs are 3 colorable on orientable surfaces. So that's a very nice result. And then it turns out, so no actually for non-orientable, but yes for orientable. And it turns out there is a Polytime algorithm to decide for any surface the 3 colorability for triangle-free graphs, and also by Dvorak, Kroll, and Thomas. Again, this was this work of theirs. It's really a series of like 7 papers that also proves Havel's conjecture we mentioned for the plane, And so it kind of started in 2008 and is ongoing, but in 2009 they had written up the algorithm. Okay, so then that's large girth. In my last slide, let me talk about list coloring. So what about for list coloring? So do all of these extend, right? So we talked about on the plane about coloring and girth, higher girth, and list coloring as well. What about for the surface stuff? Well, you need a new definition of critical, right? So what is the reason? So we say a graph G is k-list critical if there's a k-1 list assignment L, such that G has no L coloring, but every proper subgraph of G does. Okay, so then is that the right definition? Well, you could have also defined it as kind of has high list chromatic number and every smaller one does not, but this kind of is nicer because it's actually more to the list assignment, right? So it'd be, if you want to do algorithms for testing, if you want to decide you're kind of colorable from that list, this is the more general and appropriate definition. So are there finally many k-list critical graphs? And the answer turns out to be yes. And it's yes for k is at least 7. So if you're doing 6 list coloring, then it's yes for k is at least 7. Sorry, you don't need a triangle free there. It's just fairly easy to do. For k equals 6, we established that that is true. So Robin and I, and it's a 200+ page proof, so obviously won't be doing that. For k equal 5 and triangle free, it's fairly easy. And then for k equal 4 and girth 5, I did that and just getting published now. And that's again a 50+ page proof, so quite long altogether. And so then you can go ahead and do algorithms and locally planar from all this. And also all those other questions for planar graphs, you know, the exponentially many colorings, the pre-colored vertices, the cycles far apart, that stuff. The crossings, that all actually works on surfaces and for lists, so all of that just kind of goes through and if you ask the right questions and right versions. So this was just a window into coloring graphs and surfaces. We have the old very nice results of Haywood and Ringel and Young's matching it, which really established that maximum chromatic number. But then we looked into this modern paradigm developed by Thomason about, you know, is that really a satisfactory answer? Maybe there's only finitely many reasons you're not. Maybe locally planar graphs are actually colorable with few colors. Maybe it's easy to decide. And it turns out the answers are kind of yes to most of these, at least for 5 or 6. But things like the 4-color theorem in those senses don't maybe generalize to surfaces. So really figuring out the truth of the matter for all these things. So again, I think that's a nice story that as mathematicians, maybe we shouldn't be happy even with some 100-year-old plus question when we resolve it, because maybe leads to further questions. Maybe we could hope for more and ask for more. So we've talked about that and surfaces. We'll talk about surfaces a little bit more when we talk about minors in the following weeks. But this concludes our coloring section. So we've gone through lots of coloring, from vertex coloring with Brooks' theorem and beyond, to edge coloring with Vizing's theorem and beyond, to list coloring with Thomason's theorem, and then coloring planar graphs, and now coloring graphs on surfaces. And so we've really shown off a lot of different coloring results as our fundamental first area in this course on graph theory. For the rest of the term, we'll be moving on to minors and then extremal graph theory and so on. But I hope you've enjoyed coloring so far, and until next time, see you then.